supposed to do log base 3 of x. So remember, when we're graphing y equals 3 to the x, we only really need to plot 2 points. We need to plot a point that makes the exponent 0 and a point that makes the exponent 1. Well, in this case, it's pretty easy because our exponent is just x. If I want to make x 0, I just make it 0. If I want to make it 1, I just make it 1. The only time it's going to change is, say I have like 3 to the x minus 1, right? Then if I wanted to make it 0, I'd put a 1 in. And if I wanted to make it 1, I'd put a 2 in. All right, but in this case, it's just an x. So I plot those. And the whole point of doing that is, well, 3 to the 0th, anything to the 0th power is 1. And anything to the first power is itself. So we're going to plot the point 0, 1 and 1, 3. Now, we know we're going to have a horizontal asymptote at y equals 0, because the only time we don't is if it moves up or down. So we're going to have a graph that looks like this, with a horizontal asymptote. Two addendums onto this. Our domain is always negative infinity to infinity for exponential functions. And our range for this one would be from 0 to infinity. Remember, range is the only one you use your y values for. Increasing, decreasing domain, you use x values for. Range goes from 0 to infinity. It's the only one that uses y values. All right, there's a reason why I picked this next one. Remember, when we're graphing logarithms, we really want to find those points of its inverse, because that's our exponential graph, which is easy to find the points. We find our exponential inverse graph, and then we just flip the points. So let's go ahead and do that. So if I was going to look for the inverse of this, so when I'm graphing a logarithm, I'm actually looking for its inverse. So the inverse of this would be x equals log base 3 of y. I would solve for y by raising everything to a base 3 exponent, which would cancel out my log base 3, and I'd be left with y equals 3x. But rather than having a y, I'm going to say, well, f inverse is going to equal 3 to the x. So I recognize that it is the inverse. Well, hey, that's that. We already found the 2 points. All we need to do is flip those 2 values, right? For the inverse values, if I'm looking for x and f inverse x, we already found those values as being 0, 1, and 1, 3. To get the values I actually want to graph, which are my x and y values, we just flip all the values to be 1, 0, and 3, 1. So I'll plot the point 1, 0, and 3, 1. Logarithms have a vertical asymptote. So we'll have a vertical asymptote at x equals 0 unless it shifts left or right. And so our graph's going to look like that. There's a slight shortcut if you're really good at this. Note that the inverse of y equals log base 3 of x is 3 to the x. This right here shows you what your inverse is going to be. This is basically our 3 to our x. So without doing a ton of work, I would already know, hey, plot the points of 3 to the x, and then take the inverse of it. Yes?
On a test, can we do that right away, or do we have to show it?
You don't have to show any work. Honestly, when I do this, I don't even do a bunch of work. I just know it's 3 to the x and it's 0, 1, 1, 3, and I just flip the 2 points in my head. Just make sure you're correct. All right, questions on that? So the easiest way to graph a logarithm is to plot the points of its inverse, which is an exponential graph, and then flip the points. Are we all okay with that? Guaranteed that's on the quiz tomorrow. Guaranteed it. All right, were there any questions from the homework? Okay. The big thing about today is just solving logarithmic equations. So we're just going to go through a bunch of different methods on how we solve logarithmic equations. I think the biggest thing we have to note today is this note that I put right here. We didn't really talk much about it because we just didn't have the time because we're really up against the wall. But the fact is, if you have log base b of x, both b and x must be positive. So whatever's inside here has to turn out to be positive. And our bases, like this 2, 2, and 2, those all need to be positive as well. So whenever we're solving for these, make sure you're checking to make sure if I plug it back in, everything stays positive. If it ever turns one of those two things negative, it's not a solution. All right, so even if while we're solving it, we come out to -2, and I plug -2 in for here, and I come out to -5, I'm like, that's not a solution because it would make this inside part negative. So that's the big thing here. We're going to solve, and we're going to check to make sure it doesn't make anything negative. All right, so we have log of x minus 3 equals 4. Well, that's just log base 10. I'm always interested in getting this part out, so I want to cross out that log right here. Well, since this is log base 10, I'm going to use an exponent base 10. So nothing weird is going to happen here. It's just what we've been doing. I'm going to raise everything to a base power of 10. So I have log base 10 to the x minus 3 equals, and I do that to the same other side, 10 to the 4th power. And I do that because I have log base 10. The exponent base 10 will cancel out the log base 10. Yes, Liam?
So if it was like log base 4 or something, you would just put 4 raised to log base
4, yep. And we know it's log base 10 because I didn't put anything here, so it automatically has to be log base 10. Automatically has to be. So we just have x minus 3 equals 10 to the 4th is just 10 with 4 zeros, or 1 with 4 zeros, I should say. Add 3 to both sides, and we have x equals 10,000. Three.
That's pretty easy. That was big time easy.
Yeah, they're not supposed to be hard.
Your partner just hard. You're my favorite partner. You're my favorite partner.
All right, our next one.
My life partner.
Whenever we have a problem that we're trying to solve for x's, we are going to condense it. We are going to condense it first and then see what happens from there. So I'm just going to condense the left-hand side. If I need to, I'll bring the other side over, but I'm just going to condense the left-hand side first. So to condense the left-hand side, I'm going to notice this plus. That is that product property, where if I'm adding two logarithms of the same base, I could turn it into multiplying the arguments. So rather than having two things here, I'm going to change it to log base 2 of the first argument, x. I should use brackets instead of double parentheses. I'll do x times x plus 2. So it's argument 1 times argument 2 equals log base 2 of 6 plus 1. This right here is a one-to-one statement. I have log base 2 of something on one side and log base 2 of something on the other side. So that is known as our one-to-one. If it's one-to-one, I can jump right and say what's inside here has to equal what's in here. In other words, if this is log base 2 of 2, this side also has to be log base 2 of 2. They have to be the same number. So this has to be the same as this. If you forget that on the quiz or on the exam, your next step would be to raise everything to an exponent base 2, and both your logs would cancel out anyway. So no matter how you solve this, the logs will cancel out. I'm going to use the one-to-one property, which says that this inside must equal that, because they are the same base on the outsides. So we're just going to have, and I'm going to distribute too, so I'm going to have x squared plus 2x must equal 6x plus 1. Now let's move everything to the left-hand side, which will give me x squared minus 4x minus 1 equals 0. It's not factorable. It's not factorable because I can't think of two numbers that multiply together to give me 1 and then add together to give me 4. So it's not factorable. On the test, quiz, exam, don't just say it's not factorable and quit. Because we always have that cure-all for all quadratic equation. And what is that called?
Quadratic formula.
The quadratic formula. So we're going to plug this in the quadratic formula, which is x equals negative b, so negative 4, plus or minus the square root of b squared minus 4ac all over 2a. Well, 4 squared is 16. And then it's going to be plus 4. So that's going to be 20. So let's go here. That's going to be positive 4 plus or minus the square root of 20 over 2. Well, we can simplify the square root of 20. We could simplify that as, so let's continue down here. We'll have 4 plus or minus, well, the square root of 24 goes into the square root of 20, so I can reduce that to 2 square root of 5 over 2. Divide both of these numbers by 2 to give me 2 plus or minus the square root of 5. Let's go back to that thing I circled. Note, our bases cannot be negative. Well, I'm not trying to change my bases. They stayed at 2, so that's fine. X must also be positive. So this x must be positive when I plug it in. So let me highlight that. Where's my highlighter? So that x needs to be positive if I plug it in. This needs to be positive if I plug it in. And this needs to be positive if I plug it in. Well, 2 plus square root of 5, that's going to make all those positive. But what's 2 minus square root of 5 equal? It's going to be a negative number. Am I allowed to plug a negative in for that x right there?
No.
No, I'm not. So is 2 minus square root of 5 a possible answer?
No.
Nope. So the only answer we actually have is 2 plus square root of 5. 2 minus square root of 5 does not work because when I plug it back in, it makes my argument negative. So I would always, if I came out with this answer, I'd do exactly what Caitlin did. Plug in my calculator, make sure it comes out to a negative number. If both of them would be positive, which can happen, it could be 4 minus square root of 5, which would be a positive. Both of them will work. All right, continuing on. Once again, if I have two logarithms put apart on one side, I'm going to put them together. This is going to be the quotient property. I have two logs of the same base being subtracted. So I'm going to make that log of x divided by x minus 1 is going to equal 2.
Wait, what? Isn't it when it, oh, never mind.
Nope, it's fine. They both have the same base. We're subtracting. I'm going to use that quotient property, which says divide our arguments. All right. Now I need to get rid of that logarithm. I need to get rid of that logarithm, and I know if it doesn't have a base, it's automatically base 10. So I'm going to raise everything to an exponent with base 10. So I'll raise the left side to base 10 x over x minus 1. Equals, do the same to the other side, raise it to a base 10. Log base 10 and an exponent with base 10 are going to cancel each other out. And I'll be left with x divided by x minus 1 equals 100. Now it's just a normal problem to solve. I have x over x minus 1. I want to get rid of this fraction. So I'll multiply both sides by x minus 1. So our next step would be to have x equals 100 times x minus 1. Distribute the 100. We'll have x equals 100x minus 100. Move all of our x's to one side and all of our whole numbers to another side. So I'll have negative 99x equals negative 100. Divide by negative 99 on both sides. We'll come up with x equals positive 100 over 99. So really the key is just how do I get rid of those logarithms and then solve it like normal. All right, the last one on the page. Like I said, your goal is to condense and then see where you go from there. Well, condensing includes putting our square roots in the right places, or our powers in the right places, and to combine things on the other side. So what I'm looking for here is I'm going to say, well, 2 doesn't have to stay in front. I can throw that up as a power. So on the left-hand side, I could change that to ln of x squared. On the other side, I have ln of x plus 3 plus ln of x minus 1. Those have the same base, log base e, and they're being added, so I can use the product property. The product property says multiply the arguments. So we are going to now have x plus 3 times x minus 1, all with one natural log out front. Once again, this is 1 to 1. If that's all I have is one logarithm of the same base on both sides, I could say what's inside has to be equal. And if you did not catch that, you would raise both sides to base e, and our ln's would cancel out anyway. All right, so if you didn't catch the 1-to-1 while solving it, they should cancel out. But I'm going to use the 1-to-1 property, say, well, that means that x squared equals, I'm going to do some distributing. X times x would be x squared. 3x minus 1x would be plus 2x. 3 times negative 1 would give me negative 3. Cool. Solve it like normal. Let's move this x squared to this side by subtracting. So I'll subtract x squared from both sides. That'll give me 0 equals 2x minus 3. Add 3 to both sides. I'll have 3 equals 2x. Divide 2 on both sides. And we're going to come up with x equals 3 divided by 2.
Can you just really quickly go over why it's 1-to-1 again? I didn't catch that.
Anything that has so if I have log base b of something equals log base same b of something, that means that x has to equal y.
Oh, okay. Yeah.
It has to be, because it has to be the same number in here as here. So if I'm doing the same function on this side, right, I'm taking log base e of something, this right here has to be the same number as this for them to result in the same thing.
Oh, all right.
Does that make sense?
Yeah.
Okay. Because the same thing's happening to this as this, so they have to be equal. But Liam, like I said, let's say you forget about the 1-to-1 property.
You just multiply those bad boys?
We're not multiplying them. How do I get rid of a natural log?
You multiply it, or you
Raise it.
raise it to the 10.
Not to 10.
To e.
To e, because this is e. So if you would do that, if I'd raise this one to a base e, this one to a base e, all those ln's would cancel it, natural logs would cancel out, and you'd be left with that 1-to-1 property anyway. So even if you don't recognize the 1-to-1 property, you should still be able to solve this because you go, okay, raise it to a base e, boom, gone. Oh, they're gone. They're both gone. I'm just left with that. All right? So even if you don't recognize that 1-to-1, you can still solve it. All right, last two. These are going to be kind of how we solved yesterday's. What I'm going to do is I'm going to take log base 10 of both sides. So I'm going to take log base 10 of both sides of these. And we'll see why in just a second. So I'm going to take log base 10 of 1.02 to the 4t minus 1 is going to equal log base 10 of 5. Now, the whole reason I did that is to move this exponent, because now we have the power property that says now I can move that out front. I can now move that out front. So that's going to give me 4t minus 1 times that log of 1.02. And that's going to equal log of 5. Note that this is multiplication. We have 4t minus 1 times log of 1.02. So what I'm going to do is I'm going to divide both sides by log 1.02 so that this would cancel out, that would cancel out. And I'll do the same thing to the other side. Log of 1.02. That's going to leave me with 4t minus 1 equals log of 5 over log of 1.02. Well, look at this. I could plug this in my calculator, right? Because we have a dedicated log button. So this is just a number I can use my calculator for. So now all I have to do is add 1 to both sides and then divide everything by 4. So this is a number I can plug in my calculator, add 1 to both sides, and then divide everything by 4. So we're going to end up with t equals log base 5 over log of 1.02 plus 1 all over 4, which is something you can plug in your calculator, which I strongly encourage you try to do. Make sure you can get this right. But you should come up with about 20.5685. Our last one's nearly the same problem. However, what I want you to use in the next one is I want you, rather than using log on both sides, I want you to use ln on both sides, just to get in the habit of using natural log. Sometimes it's easier to write ln than log. So we're going to do ln of 3 to the 2x minus 1 equals ln to the 5 to the x. And I'm going to let you complete this, because there's two ways you can do this one. So we have ln, and we're going to bring out that 2x minus 1 out front. And we're going to bring that x out front. So that's going to give me 2x minus 1 times the ln of 3 is going to equal, when we bring that x out front, ln of 5. So this one's different because we do have an x on both of them. So there's two ways we can do it. First way is so both ways are going to start here. You have to make sure you have this correct. So you have to have parentheses around the 2x minus 1. So each way is going to branch out from here. Let's go through both ways. First way is factoring. So in order to factor, I would need to distribute this ln to both of them, which would give me 2x ln of 3. So that's the only thing yours was missing, Mike. Minus ln of 3. And then I would go ahead and move the other x to this side, which would be minus x ln of 5 equals 0. Because whenever I have x's in two places, it's always our goal to get all of our x's on one side, Liam. Let's leave our hood alone. Get all of our x's on one side. So I'm looking at my x's, and I'm saying I want this x and this x on the same side, which means I want to move this to the other side. So I would add ln of 3 to both sides to give me 2x ln of 3 minus x ln of 5, and that's going to equal ln of 3. All right, now that I have the x's, I can now factor them out. I can factor an x out of both of these, which will give me x of 2 times ln of 3 minus ln of 5 equals ln of 3. Then I would divide both sides by this whole thing. I would divide both sides by that whole thing to give me x equals ln of 3 over 2 times ln of 3 minus ln of 5. And that's going to come out to about 1.8691. Any questions of what I just did there? I fully expect you to be able to do that. There is another method to it. So I'm going to wait till everyone has this. Does everyone have this written down if they wanted to? Are we all good? Liam, you good? Okay. Here's another way to do it. So I'd pay attention. This is the way that Mikey did it. The only thing Mikey did is he rounded a little bit early, so he came up with a slightly different answer than I did. So what you can do is rather than distributing this, I can just go, well, I'll divide both sides by x, and then I'll divide both sides by this ln of 3, which would give me 2x minus 1 over x equals ln of 5 over ln of 3. The big thing to recognize is ln of 5 over ln of 3 is just a number. And in fact, this is where Mikey just rounded it. He put it in his calculator and rounded it, so he just saw that it was just a regular number. Well, I'm going to leave it as is. And what I'm going to do is I'm going to multiply both sides by x to give me 2x minus 1 equals ln of 5 over ln of 3. Maybe I'll put that in parentheses. X. Well, once again, that's just a number times that. It's like 2x. It's like 2x is just the number x. Well, that means I just need to add 1 to both sides to give me 2x equals this number, right? ln 5 over ln of 3. X plus 1. Well, right here might be a good time to approximate that. Mikey, what did that come out to about? 1.8. No, not your final answer. What was ln of 5 over ln of 3?
1.4649.
1.4689?
1.649.
Do one more time, sorry. 1.6.
Oh, 1.4649. 4649.
I have too many numbers happening. Okay, 4699. Okay. X plus 1. All you need to do is subtract this 1.4699 from both sides and then divide what's left over. I prefer the other method because you're not rounding too early, but this method works and would be fine for our answer.